We move out of the laboratory and into the factory and construction site, showing exactly why an engineer chooses one path over another. First, let's look at annealing in action. You can see the sleek curves of car body panels and kitchen sinks. These are made from deep-drawn sheet metal. Because the annealing process makes low-carbon steel incredibly soft and ductile, the metal can be stretched and formed into these complex, deep shapes without tearing or cracking. Without annealing, the steel would be far too stiff to ever achieve these designs. Next, we look at normalizing in action, which is the backbone of heavy industry. For structural steel, like the massive beams and plates used in bridges and skyscrapers, normalizing is essential. It ensures the metal has a uniform, stable structure, which is critical after the intense heat and stress of welding or fabrication. You also see large forgings, such as heavy-duty crankshafts and axles. These parts are normalized after the forging process to relieve internal stresses. This doesn't just make them more stable, it prepares them perfectly for the final machining and hardening steps that follow. Whether it's the thin skin of a vehicle or the massive bones of a bridge, heat treatment is what ensures the material is up to the task. We conclude our look at real-world applications with the processes that define high-performance engineering: hardening, tempering, and case hardening. While our previous slide focused on making metal easy to form or stable for building, this slide is about creating tools and components that can survive the toughest working conditions on the planet. First, let's look at the power couple of metallurgy, hardening and tempering. Consider cutting tools like drills, knives, and razor blades. These must be hardened to ensure they maintain a microscopic sharp edge that won't dull. However, they are simultaneously tempered so they don't chip or shatter the moment they strike a hard surface. You see the same balance in machine parts and hand tools like hammers and springs. By combining these two treatments, engineers achieve a precise equilibrium of strength, toughness, and elasticity, allowing a hammer to strike repeatedly without breaking and a spring to bounce back millions of times. Finally, we have case hardening, which is the secret to high-stress automotive engineering. Automotive components like gears, camshafts, and fasteners face a unique problem. They need a glass-hard surface to resist constant wear, but a tough core to handle massive engine loads. Similarly, bearings, the ball and roller bearings that keep our world moving, need an incredibly durable surface to withstand rolling friction while their core absorbs constant shock. From the sharpest blade to the most complex transmission gear, these heat treatments are what turn a simple piece of steel into a high-performance. We have spent this section exploring the how and where of heat treatment. But we must address a critical what. A metal's ability to be transformed by heat treatment is not universal. It depends almost entirely on its chemical composition. For steel, the presence of carbon is the absolute critical factor. Think of carbon as the active ingredient that allows the magic of quenching and tempering to happen. Low-carbon steels, 0.25% carbon content, these generally cannot be hardened by quenching because there simply isn't enough carbon to form that needle-like martensite structure. They are best suited for annealing and case hardening. Medium carbon steels, 0.25% to 0.6% K-borne content. This is our industrial workhorse. These steels are highly responsive to hardening and tempering, providing an excellent balance of strength and toughness for parts like gears and shafts. High carbon steels, 0.6% carbon content, these can be hardened to extreme levels. They are ideal for cutting tools, dies, and springs, where maximum hardness and wear resistance are the top priorities. Beyond standard carbon steels, we have alloy steels, where elements like chromium and nickel are added to enhance hardenability, allowing for even deeper and more consistent hardening. While some cast irons and non-ferrous metals like aluminum or titanium can be heat-treated, their processes are fundamentally different from the steel cycles we've studied today. Understanding your canvas, the material you start with, is the first step in ensuring your heat treatment produces a masterpiece of engineering rather than a pile of scrap metal. We have spent this module discussing the incredible power of heat treatment to transform metal. But that power comes with significant risk. Working with extreme temperatures and flammable liquids requires unwavering attention to safety. Slide 47 outlines the strict protocols that protect you and your workshop. 1. Personal protective equipment, PPE. Before you even turn on a furnace, you must be properly armored. You must wear heat-resistant gloves and dark-tinted safety glasses or a full face shield to protect against infrared radiation and splashes. Standard clothing won't do. You need a flame-resistant apron or heavy cotton overalls to prevent burns. 2. Handling and quenching. The way you move hot metal is just as important as how you heat it. Always use tongs with a secure grip for all hot metal. Never assume a part is cold just by looking at it. Place hot parts only on designated heat-resistant surfaces, such as fire bricks or steel tables. When quenching in oil, work in a well-ventilated area to avoid inhaling fumes and always have a metal lid ready to quickly smother a potential fire. 3. Fire safety. Finally, you must be prepared for the worst-case scenario. Know the location and type of your fire extinguishers. Specifically, you need a Class B extinguisher for oil fires. Most importantly, never leave a furnace or quenching station unattended while in operation. In the world of metallurgy, a master is not just someone who knows how to harden steel, but someone who respects the process enough to stay safe every single time. As we reach the conclusion of Part 3, take a moment to look at the transformations shown here on slide 48. We began this journey looking at raw elements and industrial manufacturing, and we end with the high-precision tools that define modern life. Heat treatment is far more than just a mechanical process. It is the deliberate, controlled art of giving steel its purpose. By mastering the complex interplay of temperature and time, we are able to transform a simple, uniform alloy into a vast array of high-performance materials, each possessing a unique character engineered specifically for its task. Consider the range of what we have discussed. The chassis of a car, engineered for ductility and formability through annealing to keep passengers safe. The tip of a surgical scalpel, engineered for extreme hardness and a lasting edge through precise hardening and tempering. Industrial gears and bearings, engineered with dual properties to withstand both constant wear and heavy shock. In every instance, the soul of the steel has been precisely forged not just by a hammer, but by the scientific application of heat. You now understand that a piece of metal is not a static object. It is a canvas of potential, waiting for the right thermal cycle to unlock its true capability. We have reached the end of our journey through the world of metallurgy. Looking at our final recap, you can see how far we've traveled, from the basic classification of elements to the advanced thermal engineering of precision components. Let's review the 5 key pillars of this lesson. Metals. We began by identifying the different classes of metals and the vast array of uses in modern society. Properties of metals. We moved into the DNA of materials, exploring the physical, chemical, and mechanical properties that determine how a metal behaves under pressure. Iron making. We looked at the sources of metals and the massive scale of the blast furnace where the extraction process begins. Steel production. We traced the history of making steel, from early historical methods to the high-efficiency modern basic oxygen furnaces, BOF, and electric arc furnaces, EEAF, used today. Heat treatment. Finally, we mastered the 5 fundamental heat treatment processes: annealing, normalizing, hardening, tempering, and case hardening, and saw how they are applied to create everything from car panels to surgical scalpels. By understanding these stages, you now see that metal is not just a raw material, it is a highly engineered substance. Whether you are designing a bridge or a microscopic gear, you have the knowledge to select the right metal, produce it efficiently, and treat it precisely to ensure it never fails its purpose. That brings our exploration of metallurgy and heat treatment to a close. Thank you very much for your time and your focus today. We have moved from the raw earth to the refined, engineered components that drive our world, and I hope you now see every piece of steel through the lens of its potential. Our next session, Lesson 3, will take these engineered materials into the workshop as we explore hand tools, machine tools, and processes. We will see exactly how we shape and manipulate the metals we have learned to produce and treat.